Picture the most powerful explosion you've ever seen, maybe a thunderous fireworks display or a volcanic eruption that lights up the sky. Now, multiply that energy by a number so large it's almost impossible to comprehend. Because out there, in the vast, silent darkness of space, the universe is staging its own unimaginable light shows, events so energetic they dwarf anything we could ever recreate here on Earth. A single gamma-ray blast, lasting just a few seconds, can unleash more energy than our Sun will produce in its entire 10 billion-year lifetime. That's not science fiction. That's the raw, unfiltered power of the cosmos at work. What if I told you these explosions aren't rare? They happen all the time, scattered across the universe, hidden in the blackness between stars. Some are the death cries of massive stars collapsing in on themselves. Others are violent collisions between neutron stars, so dense a single teaspoon would weigh 1 billion tons. And then there are the mysterious, unexplained bursts of energy that appear out of nowhere, defying everything we think we know about physics. These aren't just distant curiosities, they shape the very fabric of space and time, seeding the universe with the building blocks of new stars, planets, and even life itself. Today, we're taking a journey into the heart of these cosmic powerhouses. Over the next 30 facts, we'll uncover the secrets behind the universe's most energetic events, from the moment they ignite to the way they ripple across galaxies, leaving behind clues that scientists are still piecing together. You'll discover how a single event can outshine entire galaxies, how black holes act like cosmic particle accelerators, and why some of these explosions might hold the key to understanding the birth of the universe itself. So buckle up, we're about to dive into a world where energy isn't just measured in watts or joules, but in the mind-bending scales of supernovas, quasars, and hypernovas. The universe is far wilder, far more violent, and far more brilliant than you've ever imagined. Ready to see what it's truly capable of? Let's begin. Gamma-ray bursts are like the universe's ultimate power, move blinding flashes of energy so intense they momentarily outshine everything else in the cosmos. Think about that. In just a few seconds, one of these bursts can release more energy than our Sun will over its entire 10 billion-year lifespan. That's not just impressive, it's almost incomprehensible. These explosions are so powerful they rank second only to the Big Bang itself in raw energy output. The story of how we discovered gamma-ray bursts is almost as wild as the phenomenon itself. Back in the 1960s, the United States launched a series of satellites designed to detect nuclear weapons tests. Instead, they picked up something far stranger: brief, unpredictable bursts of gamma rays coming not from Earth but from deep space. Scientists were baffled. At first, they thought it might be some kind of military secret or even a malfunction. But as more data came in, the truth became undeniable. The universe was producing these eruptions naturally, and we had no idea why. For decades, gamma-ray bursts remained one of astronomy's greatest mysteries. Were they coming from nearby or from the far edges of the universe? Were they caused by dying stars, colliding black holes, or something even more exotic? It wasn't until the late 1990s, with the launch of advanced space telescopes, that we finally got our first real clues. We now know these bursts come in two distinct flavors, long and short. The long bursts, lasting anywhere from 2 seconds to several minutes, are linked to the explosive deaths of massive stars in hypernova. The short bursts, lasting less than 2 seconds, are thought to be the result of neutron stars smashing into each other in violent, universe-shaking collisions. But here's the truly mind-blowing part: these cataclysmic events don't just vanish into the void. The energy they release travels across billions of light years, leaving behind afterglows that can be detected for days or even weeks. If one happened anywhere near our galaxy, the radiation alone could strip away Earth's ozone layer, triggering a mass extinction. Thankfully, the closest known gamma-ray burst was still millions of light years away. but it's a humbling reminder of just how small we really are in the face of the universe's raw power. If a supernova is the universe's way of going out with a bang, then a hypernova is its way of rewriting the rulebook entirely. These cosmic catastrophes are what happens when the most massive stars in existence, true giants dozens of times heavier than our sun, reach the end of their lives. But instead of fading quietly, they detonate with such ferocity that they make ordinary supernovas look like firecrackers. We're talking about explosions so powerful they can briefly outshine entire galaxies. Here's what happens during a hypernova. When these colossal stars run out of fuel, their cores collapse straight into black holes. No gentle fade out, no slow burn, just an instantaneous, catastrophic implosion that triggers an explosion of almost unimaginable scale. The energy released doesn't just blast the star's outer layers into space, it shoots twin jets of plasma out from the poles at nearly the speed of light. These jets are so intense they act like cosmic blowtorches, beaming focused energy across the universe in the form of those long gamma-ray bursts we talked about earlier. But hypernovas aren't just destructive, they're also creators. The extreme conditions inside these explosions forge elements heavier than iron, scattering them across space in vast glowing clouds. Every ounce of gold in your jewelry, every speck of platinum in a car's catalytic converter, those atoms were likely born in the heart of a dying hypernova billions of years ago. Without these titanic explosions, the universe would be a much simpler place, devoid of the heavy elements that make planets and life possible. What's truly wild is how fleeting these events are. A hypernova's brilliance might last mere weeks before fading, but its echoes reverberate across the cosmos for millennia. By studying the remnants left behind, expanding shells of gas, swirling disks of matter around newborn black holes, we get a front-row seat to some of the most extreme physics in the universe. It's like piecing together the aftermath of a cosmic bomb blast to understand what kind of explosive made the crater. And here's something that might keep you up at night: hypernovas aren't just happening in distant galaxies. Our own Milky Way has stars massive enough to go hypernova, though thankfully none are close enough to pose a threat. Still, when you look up at the night sky, remember, somewhere out there, a star is reaching the end of its life, ready to unleash a storm of energy that could rewrite the chemistry of an entire galaxy. The universe doesn't do things by halves, and hypernovas are the ultimate proof of that. Quasars are the universe's ultimate powerhouses, cosmic beacons so bright they make entire galaxies look dim by comparison. At their core lies a supermassive black hole, billions of times heavier than our sun, devouring matter at a staggering rate. But here's where it gets truly wild. As gas, dust, and even stars spiral toward their doom, they don't just vanish quietly. Instead, they ignite an inferno so intense it creates the brightest objects in the known universe. What sets quasars apart are their jets, twin beams of superheated plasma shooting out from the black hole's poles at nearly the speed of light. These aren't just narrow streams of energy, they stretch for millions of light years, far beyond the boundaries of their host galaxies. Imagine a fire hose blasting material across distances so vast it would take a beam of light, the fastest thing in existence, millions of years to travel from one end to the other. The energy behind these jets is almost incomprehensible. A single quasar can outshine 1,000 Milky Ways combined, and its jets act like cosmic particle accelerators, hurling electrons and other particles across the universe with enough force to glow in X-rays and radio waves. Scientists believe magnetic fields, twisted into unimaginable shapes by the black hole's rotation, act like cosmic slingshots, launching matter into the void with pinpoint precision. But quasars aren't just dazzling light shows, they're also time machines. Because their light takes billions of years to reach us, studying them lets astronomers peer back into the universe's infancy. The most distant quasars we've spotted existed when the cosmos was less than 1 billion years old, revealing how supermassive black holes grew so enormous so quickly. It's a puzzle that challenges everything we thought we knew about cosmic evolution, and here's the kicker: quasar jets aren't just relics of the past. They're still shaping the universe today. By blasting energy and matter into intergalactic space, they heat surrounding gas, preventing it from cooling and forming new stars. In a way, these jets act like cosmic regulators, controlling how galaxies grow and evolve over billions of years. So the next time you gaze up at the night sky, remember, somewhere out there, a quasar's jet might be carving a path through the darkness, steering the fate of entire galaxies with nothing but pure, raw energy. There are stars, and then there are stars that defy every law of physics as we know them. Meet the Magnetar's neutron stars, so dense a sugar cube-sized chunk would weigh as much as a mountain, and with a magnetic field so strong it could rip the atoms right out of your body from halfway across the Milky Way. These cosmic powerhouses are nature's ultimate electromagnets, packing a magnetic force a quadrillion times stronger than Earth's. To put that in perspective, if a Magnetar appeared as close to us as the Moon, its magnetic field would erase every credit card on the planet in an instant. But what really sets Magnetars apart are their tantrums, violent starquakes and flares that unleash more energy in a split second than our Sun emits in 100,000 years. Picture this: the crust of a neutron star, under unimaginable pressure from its own gravity, suddenly cracks like an eggshell. The result, a quake so powerful it sends shockwaves rippling through the star's magnetic field, twisting it like a rubber band until it snaps. When that happens, the Magnetar unleashes a flare of gamma rays and X-rays so intense it can light up the entire galaxy for a heartbeat. And here's the eerie part: we've felt their fury. In 2004, a Magnetar flare 50,000 light-years away bombarded Earth's upper atmosphere with enough radiation to briefly ionize it, disrupting radio communications worldwide. Astronomers actually watched as the blast distorted our planet's magnetic field, triggering auroras near the poles. For a moment, a dying star's death throes reached across interstellar space to shake hands with our own planet's defenses. The craziest part: Magnetar flares might be responsible for some of the mysterious gamma-ray bursts we've detected over the years. While most bursts come from colliding neutron stars or hypernovas, a handful have all the hallmarks of a Magnetar's violent outburst. It's a reminder that even in the vast emptiness of space, invisible forces are at work, forces so powerful they can reach out and touch us from the other side of the cosmos. So next time you look up at the night sky, remember, somewhere out there, a Magnetar might be winding up for another cosmic temper tantrum, and when it lets loose, the universe itself takes notice. Our Sun may seem constant and reliable, but don't let its steady glow fool you. It's capable of tantrums that could send civilization back to the Stone Age in minutes. While we often think of solar flares as harmless bursts of light, the truth is far more terrifying. Take the Carrington event of 1859, when a solar superflare slammed into Earth with such force it set telegraph stations on fire without a single wire touching another. Operators reported sparks leaping from their equipment, papers igniting on desks, and some even receiving shocks just from standing near the machines. This was long before smartphones, satellites, or power grids, yet the flare's impact was so powerful it lit up the skies from the Caribbean to the Rockies with auroras so bright people could read newspapers at midnight. Fast forward to today, and a flare of that magnitude wouldn't just fry telegraph lines. It would cripple modern life. Imagine a pulse of energy so intense it overloads every transformer on the planet, frying power grids like a surge through an unprotected computer. Within seconds, lights go out, refrigeration stops, cell towers fail, water pumps shut down, hospitals scramble for backup generators, but even those might not survive the electromagnetic onslaught. Satellites, blinded by the radiation, tumble out of orbit, wiping out GPS, weather forecasting, and global communications. The damage could take years, maybe decades, to repair, with economists estimating costs in the trillions. What makes this even scarier, the Carrington event wasn't unique. Ice cores and tree rings reveal evidence of even larger solar storms in Earth's past, like the Miak event around 12,000 years ago, which would have been strong enough to strip away chunks of our atmosphere if it happened today. And here's the kicker: scientists studying other stars have spotted superflares hundreds of times more powerful than anything our sun has produced in recorded history. If one of those hit us, the consequences would make the Carrington event look like a static shock. The chilling reality is that we're overdue for another solar storm of this scale. Unlike asteroids or volcanoes, we can't see these flares coming until they're already on their way, giving us mere hours to prepare. Some countries have begun hardening power grids and shielding critical infrastructure, but progress is slow. So the next time you glance at the sun, remember, it's not just a warm glow in the sky. It's a sleeping giant capable of unleashing chaos with a single violent sneeze. And when it does, our entire way of life hangs in the balance. Black holes are cosmic vacuum cleaners, right, sucking in everything, even light itself, never letting go, except that's not the whole story. When two black holes spiral toward each other, locked in a gravitational dance, they don't just merge quietly. They rip spacetime apart, sending shockwaves across the universe that we can actually detect. These aren't ripples in water or vibrations in air. These are gravitational waves, literal distortions in the fabric of reality, predicted by Einstein over a century ago but only proven in 2015. The moment two black holes collide is one of the most violent events imaginable. Picture this: as they orbit each other, they lose energy, not through friction or heat, but by warping spacetime itself. The closer they get, the faster they spin, up to half the speed of light, until, in a fraction of a second, they slam together. The collision is so cataclysmic it converts a chunk of their combined mass directly into pure energy. How much energy? In the first detection by LIGO, two black holes 30 times the mass of our sun merged, releasing more energy than all the stars in the observable universe combined for one fleeting moment. What's wild is how we hear these events. LIGO, the Laser Interferometer Gravitational Wave Observatory, doesn't use telescopes or cameras, it listens. Its detectors, with laser beams traveling down 2-mile-long tunnels, measure changes smaller than a single atom's width. When a gravitational wave passes through Earth, it stretches space in one direction while squeezing it in another, and LIGO picks up that microscopic wobble. The signal, a faint chirp, rising in pitch as the black holes spiral closer, then a sudden silence as they merge. That chirp is the sound of spacetime itself ringing like a bell. Here's where it gets even stranger. The energy released in these mergers doesn't come from light, heat, or explosions. It's pure spacetime distortion. Imagine dropping a pebble into a pond. The ripples carry energy away from the splash. Black hole mergers do the same, but instead of water, they're rippling the universe's underlying structure. And these ripples aren't just curiosities. They've opened an entirely new way to study the cosmos, revealing black holes we'd never see with traditional telescopes, some so ancient they formed before the first stars lit up. But the real jaw-dropper: these waves travel at the speed of light, unaffected by dust, gas, or even other black holes. They're the universe's ultimate messengers, carrying secrets from the most chaotic events in existence. Every time LIGO detects a chirp, it's not just spotting a collision. It's eavesdropping on a conversation between black holes written in the language of warped space and time. And with every new detection, we're learning just how loud, how violent, and how beautiful the cosmos really is. Some of the universe's most dazzling light shows don't come from explosions. They're spun into existence by cosmic dynamos called pulsars. Imagine a neutron star spinning hundreds of times per second, whipping beams of radiation across space like a lighthouse on overdrive. But these aren't just beams of light, they're torrents of charged particles screaming outward at nearly the speed of light. slamming into surrounding gas and dust to create pulsar wind nebulae, glowing, ever-shifting clouds of energy that outshine entire star systems. Take the Crab Nebula, one of the most famous pulsar wind nebulae in our sky. At its heart lies a pulsar spinning 30 times every second, blasting out particles with such force that the entire nebula glows with the energy of 75,000 suns. The pulsar's magnetic field, 1 trillion times stronger than Earth's, acts like a giant particle accelerator, whipping electrons around until they emit eerie blue X-ray light. Watching time-lapse images of the crab, you can actually see the nebula's filaments dancing and writhing as the pulsar's wind reshapes them in real time, a cosmic ballet choreographed by raw physics. What's truly remarkable is the precision of these celestial lighthouses. Some pulsars rotate with such consistency that their pulses rival atomic clocks in accuracy. The Vela pulsar, for instance, spins 11 times per second with a rhythm so steady you could set your watch by its flashes, if your watch needed millisecond precision across thousands of years. This incredible stability comes from the neutron star's unbelievable density, packing more mass than our Sun into a sphere the size of Manhattan, creating a flywheel so perfectly balanced it barely loses speed over centuries. But the real magic happens where the pulsar wind meets interstellar space. Charged particles streaming from the pulsar collide with slower-moving gas, creating shockwaves that light up like neon signs across the electromagnetic spectrum. In some nebulae, these interactions generate gamma rays powerful enough to detect from Earth, while others glow with ethereal visible light that reveals intricate structures, tendrils, loops, and jets sculpted by magnetic fields we can barely comprehend. Perhaps most astonishing is how these nebulae evolve. Unlike supernova remnants that fade over millennia, pulsar wind nebulae can grow brighter as their central engines slow down, redistributing energy in dazzling new patterns. It's a reminder that even in death, stars don't just vanish, they transform, becoming laboratories for some of the most extreme physics in the cosmos. So the next time you see an image of the Crab Nebula's swirling tendrils, remember, you're not just looking at a pretty space cloud. You're witnessing the breath of a stellar corpse, exhaling particles at nearly light speed and painting the void with radiation. Now that's what you call going out in style. At the heart of nearly every large galaxy, there's a monster lurking, a supermassive black hole so hungry it can devour stars like appetizers. But when these cosmic giants feast, they don't just swallow matter quietly. They ignite, becoming active galactic nuclei for short, and unleash enough energy to outshine every star in their host galaxy combined. Think about that for a second, a single point of light no larger than our solar system, radiating with the power of 1 trillion suns. It's like a flashlight outshining a stadium full of floodlights. The secret behind this unbelievable brightness lies in the black hole's accretion disk, a swirling maelstrom of gas, dust, and doomed stars spiraling toward oblivion. As material gets pulled in, friction heats it to millions of degrees, causing it to glow fiercely across the entire electromagnetic spectrum, from radio waves to gamma rays. But here's the twist: not everything makes it past the event horizon. Some particles get caught in magnetic fields so intense they're funneled into jets shooting out at nearly light speed, carving through intergalactic space for thousands of light years. These jets can pump out more energy in a single second than our Sun will produce in its entire lifetime. What's fascinating is how cyclical these feeding frenzies are. AGN don't shine steadily, they flicker like campfires in a cosmic wind. Sometimes a sudden influx of gas, maybe from a colliding galaxy or a destabilized star cluster, triggers a feeding spree, lighting up the black hole like a beacon. Other times, the accretion disk runs low on fuel, and the AGN dims to a whisper. Astronomers have even caught black holes mid-meal, watching as they rip apart entire stars in tidal disruption events, flaring brightly before settling back into darkness. But AGN aren't just celestial curiosities, they're galactic sculptors. Those high-speed jets inject energy into their surroundings, heating up gas clouds that might otherwise form new stars. In some cases, they can even starve their host galaxies of the raw materials needed for future stellar births, effectively putting a cap on galactic growth. It's a cosmic feedback loop. The black hole feeds, unleashes energy, and in doing so, controls the very environment that feeds it, the most mind-bending part. We're seeing these events unfold billions of years after they happened. The light from distant AGN has traveled so long that by the time it reaches us, the black holes responsible may have already gone quiet, their furious feasts long over. Yet their brilliance remains frozen in time, offering us a glimpse into the universe's most violent and energetic adolescence. So the next time you look up at a seemingly peaceful galaxy, remember, hidden in its core could be a sleeping dragon waiting for its next meal to wake the fire. Imagine a star something like our Sun, but perhaps much larger, wandering too close to the edge of a supermassive black hole. At first, nothing seems unusual. But then, the black hole's gravity takes hold, stretching the star like taffy in a cosmic tug-of-war. This is a tidal disruption event, one of the universe's most violent and dazzling spectacles, where a star isn't just swallowed whole, but torn apart in a brilliant, catastrophic light show. The physics behind these events is as brutal as it is beautiful. As the star approaches, the black hole's tidal forces, the difference in gravity between one side of the star and the other, overwhelm the star's own gravity. It starts to warp, then stretch until it snaps apart in a process called spaghettification. The outer layers are flung away in a fiery arc, while the rest swirls into the black hole's accretion disk, heating to millions of degrees and unleashing a blinding flare of X-rays and ultraviolet light. The aftermath, a temporary beacon so bright it can outshine the star's entire host galaxy for months. One of the most extreme examples ever recorded was Assassin 15LH. Discovered in 2015, this flare was initially mistaken for an unusually bright supernova until astronomers realized it was 20 times more luminous than the entire Milky Way. The energy released was so staggering that scientists still debate whether it was purely a tidal disruption event or something even more exotic, like a star ripped apart by a rare, rapidly spinning black hole. Either way, the numbers defy belief. Temperatures soaring to hundreds of thousands of degrees, material ejected at nearly light speed, and radiation so intense it could be detected from 3.8 billion light-years away. What makes these events so valuable to astronomers isn't just their drama, it's what they reveal. The light emitted during a tidal disruption carries fingerprints of the black hole's mass, spin, and even the star's composition. It's like getting a forensic snapshot of the destruction process, showing us how matter behaves under some of the most extreme conditions in the universe. And because these flares fade slowly, astronomers can track their evolution for years, watching as the black hole's feast transitions from violent outburst to a quiet afterglow. But here's the twist: not every encounter ends in annihilation. Some stars survive their close calls, stripped of their outer layers but still intact, like a peach pit spat out after the flesh is devoured. These partial disruptions create repeat offender stars that orbit close enough to be nibbled on by the black hole every few orbits, producing periodic flares. It's a cosmic game of cat and mouse where the mouse keeps returning, losing a little more of itself each time. The universe has a way of turning destruction into creation. The debris from these shredded stars doesn't just vanish. It seeds the black hole's surroundings with heavy elements, enriching future generations of stars and planets. So while the star's fate may be tragic, its legacy echoes across the cosmos, a reminder that even in chaos, there's a strange kind of order, one flare, one disruption at a time. Every second, Earth is bombarded by invisible bullets from deep space, cosmic rays packing enough punch to rival a professional fastball. These aren't just stray particles, they're atomic nuclei, often protons or heavier elements, hurled across the universe at nearly light speed. When one slams into our atmosphere, it triggers a cascade of secondary particles, a subatomic fireworks show raining down unnoticed around us. But the real mystery isn't their arrival. It's where they come from. Some cosmic rays are local, spat out by our sun during solar flares. Others originate within the Milky Way, launched by supernova remnants or pulsars. But the most energetic ones, the ultra-high-energy cosmic rays, defy explanation. These rare projectiles carry as much energy as a tennis ball served at 100 miles per hour, all concentrated into a single particle smaller than an atom. To reach such mind-bending speeds, they must have been accelerated by something far more powerful than a dying star. The leading suspects, active galactic nuclei, where supermassive black holes whip particles into cosmic escape velocity, or perhaps colliding galaxy clusters creating shockwaves across intergalactic space. The challenge in tracking these particles is their sheer rarity. At the highest energies, only a handful strike each square mile of Earth's atmosphere per century. When the Pierre Auger Observatory in Argentina detected one in 2021, its energy rivaled the world's most powerful particle accelerators. Nature had done in deep space what we need a 17-mile underground ring to achieve. Yet despite their energy, cosmic rays can't point back to their birthplaces. Charged and battered by magnetic fields during their epic journeys, they zigzag so unpredictably that tracing their paths is like trying to follow a ricocheting bullet in a hurricane. What makes these particles truly fascinating is how they've shaped science. Their discovery in 1912 upended physics, proving Earth isn't shielded from the cosmos' violence. Today, they serve as natural laboratories, letting us study particle interactions at energies we could never replicate on Earth. Some theories even suggest the highest energy rays might be signatures of exotic physics, decaying supermassive particles from the early universe or defects in spacetime itself. So next time you feel a raindrop, consider this. Alongside it, unseen particles from across the cosmos are striking your skin, a silent reminder that the universe is always speaking, even if we're still learning how to listen. A supernova doesn't just destroy, it creates. When a massive star explodes, the blast doesn't merely scatter debris into the void. It sends shockwaves rippling through nearby gas clouds with enough force to sculpt entire stellar nurseries. Think of it like a cosmic snowplow, compressing loose gas and dust into dense pockets so tightly packed they collapse under their own gravity, igniting the birth of new stars. This explosive recycling program is how dead stars give rise to the next generation, and few places illustrate this better than the Crab Nebula. The Crab story begins in the year 1054, when Chinese and Arab astronomers recorded a guest star so bright it was visible in broad daylight for nearly a month. What they witnessed was a supernova, the violent death of a star roughly 8 to 10 times more massive than our Sun. Today, nearly 1,000 years later, the aftermath still glows, with tendrils of gas expanding outward at over 3 million miles per hour. But here's where it gets fascinating. Those raging shockwaves aren't just expanding mindlessly. They're plowing into surrounding interstellar material, squeezing it so intensely that astronomers have spotted dense knots within the nebula regions where gas is collapsing into protostars. The physics behind this stellar rebirth is astonishing. A supernova shockwave travels so fast, often thousands of kilometers per second, that when it hits a gas cloud, the compression happens almost instantaneously. Gas that might have drifted loosely for millions of years suddenly finds itself crammed together, triggering a runaway effect where gravity takes over. The densest regions become stellar embryos, drawing in more material until nuclear fusion ignites in their cores. It's like flicking a domino. One catastrophic event sets off a chain reaction of creation. But the Crab Nebula isn't just forming any stars. The extreme conditions within these shock-compressed regions favor massive, short-lived stars, the kind destined to explode as supernovas themselves one day, continuing the cycle. This feedback loop is how galaxies grow and evolve, with each stellar explosion enriching the cosmos with heavier elements while kickstarting new rounds of star formation. Without supernovas, the universe would lack the raw materials for planets, life, and even the atoms in your body. Perhaps most remarkable is how we're seeing this process unfold in real time. Modern telescopes can pinpoint shockwaves interacting with gas clouds, watching as they glow brighter in X-rays or infrared as compression heats them up. The Crab's pulsar, the crushed core of the original star, adds another layer, blasting the surrounding nebula with a particle wind that keeps the shockwaves energized. It's a cosmic experiment playing out across a 1,000-year canvas, proving destruction and creation aren't opposites, they're two sides of the same stellar coin. Deep in our own Milky Way, far from the supermassive black holes that power distant quasars, there exists a scaled-down version of these cosmic powerhouses, microquasars. These aren't galactic-scale monsters, but stellar mass black holes or neutron stars gorging on material stolen from a companion star. What makes them extraordinary isn't just their appetite, it's their ability to launch jets of plasma at nearly the speed of light, mimicking their gigantic cousins in spectacular fashion. Take the famous microquasar SS433. This system, located about 18,000 light-years away, consists of a black hole roughly 15 times the mass of our Sun locked in a deadly tango with a nearby star. As gas gets stripped away from the star, it spirals into a glowing accretion disk around the black hole, but not all of it falls in. Some gets channeled into twin beams of superheated particles, accelerated to 99% light speed by magnetic fields twisted tighter than a corkscrew. These jets punch through interstellar space for light years, glowing brightly in radio waves as they go. What's mind-bending about these jets isn't just their speed, it's how they flicker. Unlike the steady beams from quasars, microquasar jets often come in rapid-fire bursts, flaring and dimming over weeks or months as the black hole's feeding rate changes. Astronomers have watched SS433's jets wobble like a spinning top, their orientation shifting as the black hole's rotation drags spacetime itself into a whirlpool around it. This isn't just a light show, it's real-time proof of Einstein's general relativity playing out in our cosmic backyard. The energy packed into these jets defies belief. During outbursts, a single microquasar can outshine our Sun by a factor of millions, with the jets acting like cosmic blowtorches that heat surrounding gas to X-ray, emitting temperatures. In 2019, observations of the microquasar V404 Cygni revealed jets so powerful they were visibly pushing interstellar gas aside, creating bow shocks that lit up like interstellar fireworks. But here's the real kicker: microquasars might hold the key to understanding their larger cousins. Because they evolve over human timescales rather than cosmic ones, we can watch an entire cycle of activity, from quiet periods to explosive outbursts in just years or decades. It's like having a scaled-down laboratory for studying how black holes interact with their environments, complete with jets we can track from launch to impact. So the next time you hear about distant quasars lighting up the early universe, remember, their miniature counterparts are right here in our galaxy, putting on the same dazzling show in fast forward. And in their relativistic jets, we're seeing the universal physics of black holes writ small, proving that sometimes the most profound cosmic truths come in surprisingly compact packages. When two neutron stars, cosmic remnants so dense that a sugar cube's worth would outweigh Mount Everest, spiral toward each other, they don't just collide. They detonate in a cataclysm called a kilonova, an explosion so potent it forges the universe's heaviest elements in its wake. Picture this: two city-sized objects, each crammed with more mass than our Sun, whirling around each other hundreds of times per second before smashing together. The impact unleashes a fireball of neutron-rich material, triggering rapid nuclear reactions that churn out gold, platinum, and uranium like a cosmic mint. The first time humanity witnessed this spectacle was in August 2017, when gravitational wave detectors LIGO and Virgo caught the ripples from an event dubbed GW170817. For the first time, we didn't just hear the universe's violence, we saw it. Telescopes worldwide swiveled toward the source, capturing the kilonovas' glow in unprecedented detail. The aftermath revealed something extraordinary. The infrared light wasn't just heat from the explosion. It was the literal glow of freshly minted heavy elements, their atomic nuclei freshly forged in the neutron-rich debris. Follow-up studies estimated this single event produced enough gold to outweigh Earth 10 times over, and enough platinum to fill every jewelry store on the planet. What makes kilonovas unique is their chemistry. Unlike supernovas, which create lighter elements like oxygen and silicon, kilonovas excel at building the heaviest atoms in the periodic table. Here's why. When neutron stars collide, they spray out chunks of ultra-dense matter packed with neutrons. These free neutrons get absorbed by atomic nuclei in a process called rapid neutron capture, or the R process, transforming ordinary elements into rare, precious metals. It's the universe's most extreme alchemy, happening in milliseconds under conditions no lab could ever replicate. The implications are staggering. Every gold ring, every platinum catalyst in a car's exhaust system, even the uranium fueling nuclear reactors, they all owe their existence to cataclysms like GW170817. These collisions are the universe's primary factories for elements heavier than iron, scattering them across galaxies to eventually become part of planets and life itself. But kilonovas aren't just element factories, they're also cosmic laboratories. The 1717 event confirmed predictions about gravitational waves traveling at light speed, tested Einstein's theories with unprecedented precision, and even helped astronomers measure the expansion rate of the universe. It was a single explosion that answered decades-old questions while posing new ones, like how often these events occur and whether they might be responsible for other cosmic mysteries like short gamma-ray bursts. So the next time you hold a piece of jewelry, remember, its atoms likely began their journey in a neutron star collision billions of years ago, a violent birth that echoes across the cosmos to this day. Kilonovas don't just light up the sky, they quite literally make the world we know possible. Not all jets in the universe shine equally. Some seem unnaturally bright, not because they're more powerful, but because they're aimed straight at us. Meet blazars, the cosmic equivalents of staring down the barrel of a flashlight beam from across a darkened room. These are quasars with a twist. Their relativistic jets happen to point directly at Earth, funneling an intense, concentrated stream of energy our way that outshines nearly everything else in the sky. What makes them fascinating isn't just their brightness, but their unpredictability. Unlike steady stars or even most quasars, blazars flicker wildly, flaring up and dimming over days or even hours, as if someone's playing with a celestial dimmer switch. The secret behind their erratic behavior lies in the jets themselves. As material spirals toward the supermassive black hole at the blazar's heart, some gets funneled into those narrow beams and accelerated to near light speed. But the process isn't smooth. Magnetic fields twist and snap, turbulence ripples through the jet, and shockwaves send particles careening, all of which translates to wild swings in brightness for observers on Earth. In 2018, astronomers watched as one blazar, TXS 0506+056, flared so violently it became 1,000 times brighter in gamma rays over just 2 days. But blazars aren't just dazzling light shows. They're also cosmic particle accelerators capable of something extraordinary, producing high-energy neutrinos. These ghostly particles, nearly massless and rarely interacting with matter, are famously hard to detect. Yet in 2017, the Ice Cube Neutrino Observatory at the South Pole spotted a neutrino with energy millions of times greater than anything produced in particle colliders, and traced it back to a blazar 4 billion light-years away. It was the first time we'd ever pinned a neutrino to a specific object outside our galaxy, opening a whole new window into the universe's most energetic environments. The implications are profound. Neutrinos travel across the cosmos unaffected by magnetic fields or dust, carrying pristine information about their origins. By matching them to blazar flares, we're not just studying distant black holes, we're decoding the physics of particle acceleration at energies impossible to replicate on Earth. Every flicker, every neutrino, is a clue to understanding how black holes power these jets and what happens to matter under the most extreme conditions imaginable. So the next time you hear about a blazar flaring in some distant galaxy, remember, we're not just passive observers, we're catching a beam of energy fired across billions of years, a direct message from one of the universe's most violent and mysterious phenomena. And with every pulse of light and every rare neutrino, we're piecing together how the cosmos turns destruction into illumination. Deep in the hearts of galaxies, something invisible might be tearing itself apart, releasing energy so intense we can barely comprehend it. The culprit, dark matter, that mysterious substance making up 85% of the universe's mass, yet refusing to interact with light. But what if, under the right conditions, dark matter particles collide and annihilate each other in bursts of gamma rays? It sounds like science fiction, but telescopes are actively hunting for this very signal right now. Here's how it could work. If dark matter consists of WIMP, weakly interacting massive particles as some theories suggest, these particles might be their own antimatter counterparts. When two WIMP meet in the dense cores of galaxies where dark matter is thought to cluster most thickly, they could obliterate each other on contact. The result, a flash of gamma rays, the most energetic light in the universe. Unlike ordinary matter, which glows when heated or accelerated, this would be light produced by something utterly invisible destroying itself in the dark. The Fermi Gamma Ray Space Telescope has spent over a decade scanning the sky for these elusive signals. Specifically, it's peered at dwarf galaxies orbiting the Milky Way, places rich in dark matter, but relatively free of the gamma-ray interference from pulsars and supernova. The hope was to spot an excess of gamma rays with a specific energy signature, a telltale fingerprint of dark matter annihilation. While there have been tantalizing hints, like the gamma-ray excess detected near our galaxy's center, nothing conclusive has emerged. The search continues, with each non-detection helping physicists refine their models of what dark matter could and couldn't be. What makes this hunt so thrilling is the sheer audacity of the premise. We're essentially trying to study something by watching it vanish. If dark matter does annihilate, the process would be staggeringly rare. Particles might pass through trillions of others before finally meeting their match. Yet the payoff would rewrite physics. Confirming dark matter annihilation wouldn't just solve one cosmic mystery. It would open a window into particle physics at energy scales far beyond anything our colliders can reach, offering clues about the universe's earliest moments. And here's the twist: even if we never detect it, the absence of a signal speaks volumes. It could mean dark matter isn't made of WIMP at all, forcing scientists to pivot to entirely new theories like actions or primordial black holes. Either way, the search itself is illuminating, pushing our understanding of the cosmos to its limits, one gamma ray at a time. Galaxies aren't just islands of stars, they're cosmic factories, forging elements and belching them back into the void in rivers of superheated gas called galactic superwinds. Picture a starburst galaxy where stars are forming at rates hundreds of times faster than in our Milky Way. All those young, massive stars live fast and die young, exploding as supernova in rapid succession. The combined energy of these detonations doesn't just fade into the darkness, it launches tsunamis of gas, charged particles, and heavy elements outward at speeds topping millions of miles per hour. These aren't gentle breezes, they're hurricane-force gales capable of reshaping entire galaxies. Take M82, a classic starburst galaxy just 12 million light-years away. Telescopes reveal filaments of gas stretching tens of thousands of light-years into intergalactic space, glowing in X-rays as they carry away the equivalent of millions of suns worth of material. The force behind this exodus, supernova exploding so frequently they create a collective shockwave, heating surrounding gas until it expands violently, punching through the galaxy's gravitational grip like steam bursting from a kettle. But what's truly staggering is the chemistry of these outflows. Spectroscopy shows they're laced with oxygen, carbon, and iron elements forged in stellar cores and supernova blasts, now being scattered into the cosmic wilderness. This isn't just waste disposal, it's galactic gardening. When these metal-rich winds collide with nearby gas clouds, they seed them with the raw ingredients for rocky planets and ultimately life. Without superwinds, the universe would lack the heavy elements needed to build Earth-like worlds. Even more striking, these outflows can trigger a paradoxical feedback loop. As gas is ejected, star formation slows, depleting the galaxy's fuel reserves. Yet when the wind eventually cools and falls back, it may collapse into new generations of stars, enriched with the very elements it once carried away. But here's the twist: superwinds don't just shape their home galaxies. In dense galaxy clusters, these outflows can merge, creating vast reservoirs of hot, metal-polluted gas that permeates the spaces between galaxies. The Perseus cluster, for example, contains enough intergalactic iron to forge billions of Earths, all cast adrift by ancient superwinds. It's a reminder that galaxies aren't closed systems. They're leaky sieves, constantly exchanging matter with the cosmos. The most mind-bending implication: we're seeing this process in its infancy. Some of the earliest galaxies ever observed show evidence of superwinds, suggesting this elemental recycling began when the universe was barely a toddler. Every time you breathe in oxygen or marvel at a skyscraper's steel frame, you're interacting with atoms that might have once ridden a galactic superwind across millions of light-years. The universe doesn't just create, it redistributes, ensuring no corner goes untouched by the alchemy of stars. White dwarfs are the quiet retirees of the stellar world, small, dense embers left behind when sun-like stars exhaust their fuel. But give one the wrong companion, and this seemingly peaceful object becomes a cosmic time bomb. When a white dwarf siphons too much mass from a neighboring star or collides with another white dwarf, it doesn't just flare up, it detonates in a Type I supernova, an explosion so perfectly predictable it's used to measure the universe itself. What sets these explosions apart from their core collapse cousins, the supernovas born from massive stars, is their consistency. While a core collapse supernova's brightness depends on the star's size and composition, Type I supernovas always peak at roughly the same luminosity. This happens because white dwarfs explode under very specific conditions. They're made mostly of carbon and oxygen, and when their mass creeps toward 1.4 times that of our Sun, a limit called the Chandrasekhar limit, the pressure in their cores becomes so intense that carbon fusion ignites like a runaway thermonuclear chain reaction. The entire star detonates in a matter of seconds, leaving no remnant behind, just an expanding cloud of glowing debris. This reliability makes Type I supernovas cosmic measuring tapes or standard candles. Astronomers can compare their observed brightness with their known intrinsic brightness to calculate precise distances across the universe. In the 1990s, observations of these explosions revealed something shocking. The universe isn't just expanding, it's accelerating, driven by an unknown force now called dark energy. Without Type I supernovas, we might never have uncovered one of cosmology's greatest mysteries. But here's the twist: not all Type I supernovas are identical. Some burn brighter and longer, others faster and dimmer, depending on how the explosion propagates through the star. Recent studies even suggest some might involve two white dwarfs merging, rather than a single one gorging on a companion. Yet despite these variations, their uniformity still outstrips other cosmic distance markers, cementing their role as the gold standard for measuring the cosmos. The aftermath of these explosions is just as fascinating. The debris is rich with iron, silicon, and nickel elements forged in the white dwarf's final moments. In fact, most of the iron in your blood, the nickel in your coins, and the silicon in Earth's crust likely originated in Type Ia explosions billions of years ago. It's a reminder that even in destruction, the universe is building, scattering the seeds of planets and life across the void. So the next time you hear about a standard candle supernova, remember, it's not just a measuring tool, it's a cosmic alchemist turning dying stars into the building blocks of everything we know. Imagine a black hole, something already terrifying in its stillness, suddenly flung across a galaxy at unimaginable speeds. This isn't science fiction. Rogue black holes, ejected from their homes by violent cosmic encounters, are real, and they leave destruction in their wake. Hubble's observations confirmed one such renegade in 2017, a supermassive black hole weighing as much as 1 billion suns, rocketing through space at over 5 million miles per hour. At that speed, you could travel from Earth to the Moon in under 3 minutes. What could possibly launch something so massive into motion? The answer lies in the chaotic aftermath of galaxy mergers. When two galaxies collide, their central black holes eventually spiral toward each other, locked in a gravitational dance. But if a third black hole enters the mix, perhaps from an earlier merger, the intricate ballet can turn into a cosmic shoving match. The lightest of the three gets thrown clear, catapulted away with enough force to escape its galaxy entirely. It's like a game of gravitational pinball where the stakes are a black hole's eternal exile. Hubble's runaway wasn't just speeding through space, it was trailing a wake of newborn stars. As the black hole plowed through clouds of gas, its immense gravity compressed the material, triggering star formation in a blazing corridor stretching 200,000 light-years. That's twice the diameter of our Milky Way. The shockwave of new stars, glowing blue from their youth, serves as a cosmic breadcrumb trail, pointing back to the black hole's violent ejection. It's the universe's version of a crime scene, with stellar fingerprints revealing the culprit's path. But rogue black holes aren't just fascinating oddities, they're evidence of a deeper truth about the cosmos. Their existence proves galaxy mergers aren't tidy affairs. These cosmic pile-ups leave wreckage in their wake, from orphaned stars to displaced black holes. Some theories even suggest these runaways could explain mysterious ultraluminous X-ray sources spotted in empty intergalactic space, solitary black holes, far from any galaxy, still feasting on stray gas and glowing brightly in their isolation. The scariest part, our own Milky Way isn't immune. When we collide with Andromeda in a few billion years, the supermassive black holes at their cores could engage in a similar gravitational tug-of-war. There's no telling if Sagittarius A, our galaxy's central black hole, will stay put or become a cosmic castaway. For now, though, these rogue giants remind us that even the universe's most monstrous objects aren't anchored in place. Sometimes they're sent hurtling through the void, turning the cosmos into their own personal shooting gallery. Somewhere in the distant universe, a flash of radio waves brighter than entire galaxies erupts and vanishes in less time than it takes to blink. These are fast radio bursts, or FRB, one of astronomy's most tantalizing puzzles. Lasting mere milliseconds, each burst packs as much energy as the sun releases in 80 years, yet their origins remain shrouded in mystery. What could possibly produce such intense, fleeting signals across billions of light years? The first FRB was discovered by accident in 2007, buried in old radio telescope data. Since then, we've detected hundreds more, most as one-off events, but a rare few repeating at erratic intervals. The repeater FRB 12112, for instance, fires off bursts sporadically, sometimes going silent for months before flaring up again. This unpredictability makes them maddeningly hard to study, like trying to catch lightning in a bottle while blindfolded. One leading suspect, Magnetar's those ultramagnetic neutron stars we met earlier. In 2020, astronomers got their strongest evidence yet when a magnetar in our own galaxy, SGR 1935 plus 215, emitted a radio burst eerily similar to an FRB, albeit much weaker. The key difference, this one happened close enough for us to pinpoint its source. The discovery suggested that at least some FRBs could be magnetars throwing cosmic tantrums, their twisted magnetic fields snapping like rubber bands, releasing bursts of radio waves powerful enough to be detected across the universe. But not all FRBs fit this mold. Some bursts appear too energetic for even the most unruly magnetar, sparking wilder theories, colliding neutron stars, evaporating black holes, or even hypothetical cosmic strings from the early universe. Then there's FRB 190520, which flashed from a location with no obvious magnetar nearby, deepening the enigma, the most extreme speculation. Technological signatures from advanced civilizations, though most astronomers consider that a last resort explanation. What makes FRBs invaluable isn't just their mystery, it's what they reveal about the cosmos along their journey. As these radio waves traverse intergalactic space, they interact with diffuse electrons, slowing slightly in a way that lets astronomers measure the universe's hidden matter. Each burst is like a lighthouse beam cutting through fog, illuminating the invisible gas between galaxies. Some FRBs even exhibit strange polarization patterns, hinting at traversing regions with monstrous magnetic fields, perhaps near supermassive black holes or within galaxy clusters. The hunt for answers is accelerating. New telescopes like CHIME in Canada are spotting dozens of FRBs monthly, while others are trained on known repeaters, waiting for that next burst to dissect. With each detection, we're piecing together a cosmic jigsaw puzzle, one where the pieces vanish almost as fast as they appear. Whether they're magnetars, cosmic collisions, or something entirely unforeseen, FRBs remind us that the universe is still full of surprises, broadcasting its secrets in milliseconds-long whispers across the void. Our sun may look like a smooth, glowing orb from a distance, but zoom in and you'll find its surface is anything but calm. Towering loops of plasma, called solar prominences, arc hundreds of thousands of miles above the sun's surface, structures so vast they could swallow Earth dozens of times over. These fiery filaments aren't just random eruptions, they're cosmic sculptures molded by the sun's tangled magnetic fields into shapes as intricate as they are unstable. Picture a single prominence as a colossal arch of superheated gas, held aloft not by gravity but by invisible magnetic lines. The plasma, a seething mix of charged particles, flows along these magnetic highways like cars on a freeway, tracing loops that can last for weeks before fading or erupting. At their core, prominences are relatively cool compared to the sun's corona, hovering around 10,000 degrees Celsius, which makes them appear darker against the sun's blazing backdrop. But don't let cool fool you, these structures are still hotter than the surface of most stars. What makes them truly mesmerizing is their fragility. The same magnetic fields that shape prominences can also store enormous amounts of energy, like a twisted rubber band waiting to snap. When the sun's turbulent magnetic lines suddenly reorganize, a process called magnetic reconnection, the results can be spectacular. A once stable prominence might lash outward, hurling billions of tons of plasma into space as a coronal mass ejection, or CME. These eruptions aren't just visually stunning, they're cosmic wrecking balls capable of disrupting satellites, frying power grids, and painting the skies with auroras if they hit Earth. One of the most jaw-dropping examples occurred in August 2012, when a prominence eruption sent a CME racing toward us at nearly 3,000 kilometers per second. Luckily, it missed Earth, but had it struck, analysts estimate it could have caused trillions in damage, eclipsing even the notorious Carrington event. That's the duality of prominences. They're both the sun's most beautiful and most dangerous features. The real magic lies in how they reveal the sun's invisible forces. By studying these plasma loops, scientists can map the sun's hidden magnetic skeleton, predicting which ones might erupt and which will fade peacefully. It's a reminder that even in the vacuum of space, magnetism reigns supreme, sculpting the universe not with gravity or light, but with lines of force we can't even see until they set the sky on fire. When a star explodes as a supernova, light isn't the main event, it's just the fireworks. The real show happens in the dark, where ghostly particles called neutrinos carry away 99% of the explosion's energy. These subatomic phantoms, so elusive they pass through entire planets like they're not even there, become the universe's ultimate messengers in a star's dying moments. Take supernova 1987, the closest stellar explosion observed in modern times. When light from the blast reached Earth in February 1987, telescopes weren't the only instruments that noticed. Buried deep in mines and mountains, neutrino detectors picked up 23 particles in a span of 13 seconds. That might sound insignificant until you realize these detectors normally catch maybe 1 or 2 neutrinos a day. This sudden spike was the smoking gun, proof that neutrinos had raced ahead of the light, heralding the supernova hours before telescopes saw the first glow. Here's why that's revolutionary. In a collapsing star's final seconds, its core crushes protons and electrons together, forming neutrons and releasing a flood of neutrinos. A single supernova can produce more neutrinos than there are stars in the observable universe, 10 to the 58th power of them, all launched in a brief, unimaginable pulse. These particles escape at nearly light speed while the shockwave still struggles to break free, giving us an early warning system for stellar death. But detecting them is like trying to catch smoke with your bare hands. Neutrinos interact so weakly with matter that the 1987 detection spread across 3 different experiments represented just a handful of the countless trillions that passed through Earth. The Kamiok and detector in Japan, for instance, spotted 11 neutrinos by watching for the faint blue flashes they created when hitting water molecules. Each flash represented a single neutrino interacting after traveling 160,000 light-years, a cosmic game of needle in a haystack played across intergalactic distances. What makes these neutrino bursts so valuable isn't just their early arrival, it's what they reveal about the supernova engine itself. By analyzing their energy and timing, physicists confirmed theories about how collapsing stars rebrand elements. The neutrino's heat helps re-energize the stalled shockwave, allowing it to finally explode outward and forge heavy atoms like gold and uranium. Without this neutrino-driven revival, many supernovas might fizzle, leaving behind silent black holes instead of scattering stardust across the cosmos. The legacy of 1987's neutrinos lives on in today's detectors like Super Kamiokande and Ice Cube, which stand ready for the next nearby explosion. When it happens, perhaps from Betelgeuse or another unstable giant, these silent sentinels will capture thousands of neutrinos, painting a real-time portrait of a star's death throes. It's a reminder that the universe's most violent events often speak loudest in whispers if we're patient enough to listen. The Milky Way seems eternal when we gaze up at its starry band, but this celestial giant wasn't born this vast, it grew by devouring its neighbors. Galactic cannibalism isn't science fiction. It's how our home galaxy and others like it evolved, feasting on smaller galaxies in a cosmic buffet stretching back billions of years. The evidence scattered across our skies like celestial breadcrumbs, remnants of ancient mergers that shaped the Milky Way into what we see today. Take the Gaia sausage, not a cosmic snack, but the fossilized remains of a dwarf galaxy that collided with ours around 8 to 10 billion years ago. Named for the spheroidal shape its stars trace in space and the Gaia Space Telescope that revealed it, this structure isn't just a curious oddity. It's proof of a violent assimilation, a meal so impactful it reshaped the Milky Way's very structure. The stars from this devoured galaxy move in radical, elongated orbits, cutting across the galactic disk like knives through butter, a stark contrast to the orderly motions of native Milky Way stars. These interlopers are the survivors of a galactic digestion process, left behind like bones after a feast. But the Gaia sausage isn't alone. The Milky Way's halo, the sparse outer shell of stars surrounding our galaxy, is littered with similar relics. Streams like Sagittarius, torn from a dwarf galaxy currently being ripped apart by our galaxy's gravity, snake across the sky in delicate tendrils. These aren't static scars, they're dynamic evidence of an ongoing process. Right now, the Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, is spiraling toward its eventual demise, destined to merge with the Milky Way in another 2 billion years. The mechanics of galactic cannibalism are as brutal as they are beautiful. When a small galaxy ventures too close to a larger one, tidal forces stretch and shred it, pulling stars away in long streams. Over time, these stars disperse, blending into the larger galaxy's halo while their original structure fades into oblivion. But the merger doesn't just add stars, it injects fresh gas, reigniting star formation and altering the chemical makeup of the host galaxy. The iron in your blood, the calcium in your bones, some of those atoms may have originated in a galaxy that no longer exists, delivered to the Milky Way through an ancient act of cosmic consumption. What's truly humbling is realizing this process isn't unique to us. The Andromeda Galaxy, our nearest spiral neighbor, shows its own scars of past mergers. Even giant elliptical galaxies, the titans of the cosmos, likely grew to their immense sizes by swallowing dozens of smaller galaxies. The universe operates on a simple rule: grow or be eaten. And as telescopes peer deeper into space, uncovering fainter stellar streams and disrupted dwarfs, we're finding that no galaxy, not even our own, is an island. We're all products of collision, built from the remnants of others, carrying the echoes of forgotten galaxies in every star. Imagine a bubble of perfect nothingness, expanding at the speed of light, erasing every law of physics in its path. This isn't the plot of a sci-fi movie, it's vacuum decay, one of the most unsettling theories in physics. The idea hinges on a terrifying possibility: our universe might not be in its most stable state. Instead, we could exist in a false vacuum, a precarious configuration where the fundamental fields holding reality together are temporarily stuck like a ball resting on a hilltop instead of at the bottom of a valley. One nudge, one quantum fluctuation in the wrong place, and that ball could roll downhill, rewriting physics as we know it. The trigger for this cosmic doomsday could be almost anything: a high-energy particle collision, a quantum tunneling event in deep space, or even random chance. Once initiated, a bubble of true vacuum would form where the laws of physics settle into their most stable state. The catch: this stability comes at a cost. As the bubble expands at light speed, every atom, every force, every constant we rely on would cease to function as before. Chemistry, gravity, even the speed of light itself could change within the bubble's boundaries. The shockwave wouldn't just destroy matter, it would redefine existence, leaving behind a universe utterly alien to anything we know. Here's the chilling part: we wouldn't see it coming. A vacuum decay event could start anywhere in the universe, and by the time the light from its edge reached us, the bubble itself would already be here. One moment, everything would be normal. The next, an invisible wall of rewritten physics would sweep through Earth, leaving no time for reaction or escape. It's the ultimate cosmic surprise party, except the surprise is the end of reality as we know it. The silver lining: this scenario remains purely theoretical. The standard model of particle physics suggests our vacuum is likely stable, or at least metastable enough to last billions of years. But the fact that we can even conceive of such an event reveals something profound about our universe. Beneath its apparent order lurks the potential for chaos, a reminder that even the constants we take for granted might not be as immutable as they seem. Vacuum decay isn't just a doomsday scenario, it's a humbling glimpse into the fragility of existence itself. Black holes aren't the cosmic vacuum cleaners we once thought eventually. Even they meet their end, dissolving into nothingness in a process so strange it defies classical physics. This isn't science fiction, it's Hawking radiation, a theoretical prediction made by Stephen Hawking in 1974 that turns everything we thought we knew about black holes on its head. Here's the mind-bending premise: black holes aren't completely black. Thanks to quantum mechanics, they can actually emit particles, slowly leaking energy until they evaporate entirely. The key lies in the chaotic quantum vacuum of space. Empty space isn't really empty, it's a seething sea of virtual particles constantly popping into existence in particle-antiparticle pairs, only to annihilate each other moments later. Normally, this happens too quickly to notice, but near a black hole's event horizon, things get weird. If one of these virtual particles falls into the black hole while its partner escapes, the universe essentially loses track of the energy debt, and the escaped particle becomes real, carrying energy away from the black hole. Over unimaginable timescales, this slow trickle of particles drains the black hole's mass, causing it to shrink and eventually vanish in a final burst of radiation. But here's where the paradox kicks in. According to quantum mechanics information, the fundamental details of every particle that ever fell into the black hole can't be destroyed. Yet if the black hole evaporates completely, what happens to all that swallowed matter? Does it just disappear? This information paradox has haunted physicists for decades, pitting quantum theory against general relativity in a battle for the soul of modern physics. Some theories suggest the information might be encoded in the Hawking radiation itself, scrambled like a cosmic hard drive reformatted beyond recognition. Others propose it's preserved in a mysterious remnant left behind after evaporation. The stakes couldn't be higher. If information truly vanishes, it means our understanding of quantum mechanics is fundamentally flawed. But if it's preserved, there must be hidden layers to spacetime we've yet to uncover. The irony: Hawking radiation is so faint for typical black holes that we'll never observe it directly. A stellar mass black hole would take longer than the current age of the universe to evaporate. But for tiny primordial black holes, hypothetical leftovers from the Big Bang, the final moments could be spectacular, erupting in a gamma-ray blaze equivalent to 1,000,001 megaton nuclear bombs. So while Hawking radiation might seem like an obscure quirk of quantum physics, it's actually a gateway to one of the deepest mysteries in science: how the universe balances its books. Every particle that winks into existence at a black hole's edge isn't just stealing energy, it's forcing us to rewrite the rules of reality itself. The universe began with an energy release so colossal it makes every supernova, gamma-ray burst, and quasar look like a birthday candle in comparison: the Big Bang. To quantify the unimaginable, the initial explosion packed more energy into a single second than all the stars in the observable universe would produce in their entire lifetimes combined. Picture this: a volume smaller than an atom suddenly expanding to the size of a galaxy, heating to 100 million times the sun's core temperature, and unleashing enough raw power to fuel cosmic expansion for 13.8 billion years and counting. That energy didn't just vanish, it cooled and stretched, leaving behind a faint whisper we can still detect today: the cosmic microwave background, or CMB. This afterglow, first discovered accidentally in 1965, is the oldest light in existence, a snapshot of the universe when it was just 380,000 years old. What's remarkable isn't just its age, it's how perfectly it maps the Big Bang's fingerprints. Tiny fluctuations in the CMB's temperature, no larger than 1 part in 100,000, reveal the seeds of all future structure. The slight density variations that would one day grow into galaxies, clusters, and the vast cosmic web we see now. To grasp the scale of that primordial energy, consider this. If you combined every supernova, solar flare, and gamma-ray burst ever detected, their total output would still be 1 trillion times weaker than the Big Bang's initial surge. Even the most violent modern cosmic events are mere echoes of that first cataclysm. The universe's entire history, from the formation of stars to the collisions of black holes, has essentially been a slow exhale after that first unimaginable breath. Yet the CMB isn't just a relic, it's a Rosetta Stone for cosmologists. Its patterns confirm the universe's composition: 5% ordinary matter, 27% dark matter, and 68% dark energy. Those numbers weren't guessed, they were literally written in the sky, encoded in the slight variations of this ancient light. Modern telescopes like Planck have mapped these variations with such precision that we can trace the universe's expansion down to fractions of a percent, revealing not just where we came from, but where we're headed. What's humbling is realizing we're still bathing in the Big Bang's aftermath. Every time your TV picks up static, about 1% of that snow is radiation from the CMB particles that have traveled undisturbed since the universe's infancy. It's a reminder that the most energetic event in history didn't just happen long ago. It's all around us, woven into the fabric of reality itself. The Big Bang wasn't an explosion in space, it was the explosion of space, and its echo will outlast every star, every galaxy, and every black hole the universe will ever create. The Orion Nebula isn't just a pretty cloud of gas. It's a cosmic nursery where newborn stars flicker to life amid swirling pillars of dust and plasma. At its heart lies the Trapezium cluster, a group of young, searingly hot stars whose ultraviolet radiation carves into the surrounding hydrogen like a blowtorch, ionizing the gas and making it glow with an ethereal pinkish hue. This process, called photoionization, isn't just beautiful, it's transformative, turning cold, dark molecular clouds into shimmering stellar incubators. But the real action happens where telescopes can't easily see, deep inside the nebula's dense cores, where gravity works its slow, inevitable magic. Here, pockets of gas collapse under their own weight, spinning faster and heating up until nuclear fusion ignites and a star is born. Yet these infant stars don't emerge quietly. Many of them shoot out supersonic jets of material, narrow beams of plasma that stretch for light years and slam into surrounding gas at speeds topping 150 kilometers per second. These are protostellar jets, nature's way of balancing the books. As a young star gathers mass, magnetic fields channel excess energy and material outward in focused streams, preventing the star from spinning itself apart. Where these jets collide with interstellar material, they create Herbig-Haro objects, glowing shock fronts that light up like cosmic road signs. Named after astronomers George Herbig and Guillermo Haro, these patches of excited gas act as signposts, marking where stellar tantrums meet the cold reality of space. Some, like Herbig-Haro 34 in Orion, display intricate bow shocks and knots, revealing the jet's episodic nature. Proof that young stars don't grow smoothly but in fits and bursts. What's astonishing is the sheer violence of these stellar birth pangs. A single protostellar jet can transport enough energy to power 100 suns, and the temperatures in Herbig-Haro shock fronts can soar to tens of thousands of degrees. Yet without this chaos, stars wouldn't form at all. The jets clear away excess material, allowing the fledgling star to keep gathering mass without being smothered by its own birth cloud. It's a self-regulating system where destruction and creation dance in perfect, if violent, harmony. The Orion Nebula is just one example, a nearby laboratory where we can study stellar infancy up close. But every glowing nebula, every dark dust lane, hides similar dramas playing out across the galaxy. each one is a testament to the universe's relentless creativity, where even the simplest ingredients, gas, gravity, and time, can forge something as wondrous as a star. And in their fiery outflows and glowing shocks, we're witnessing the universal rules of birth itself, written in light and plasma across the cosmos. For nearly 500 million years after the Big Bang, the universe was a lightless sea of neutral hydrogen, an era so dark we call it the cosmic dark ages. Then came the epoch of reionization, when the first generation of stars punched through the gloom like torches in a cave, their ultraviolet radiation so intense it ripped electrons from hydrogen atoms across the cosmos. This wasn't just sunlight breaking through clouds, it was a fundamental transformation of the universe itself, turning opaque fog into the transparent void we see today. The James Webb Space Telescope has become our time machine to witness this cosmic metamorphosis. Peering at galaxies like GNZ 11, which formed when the universe was just 400 million years old, Webb's infrared eyes reveal how these early stellar factories flooded space with ultraviolet photons. Unlike modern stars, which are relatively tame, these primordial giants were monsters hundreds of times more massive than our Sun, burning hot and fast before exploding as supernova. Their combined UV output acted like a cosmic blowtorch, ionizing hydrogen in expanding bubbles that eventually overlapped, clearing the intergalactic medium like morning mist burning off a lake. What's astonishing is how uneven this process was. Webb's deep field images show patches of space where reionization happened early, surrounded by regions still shrouded in darkness. It's as if the universe flickered to life neighborhood by neighborhood, with some areas remaining stubbornly opaque long after their surroundings had cleared. This patchiness suggests reionization wasn't just driven by stars. Supermassive black holes in early galaxies may have contributed. They're quasars spewing radiation that accelerated the process in certain directions while leaving shadows elsewhere. The aftermath of this epoch echoes through modern cosmology. The leftover free electrons from reionization subtly distort the cosmic microwave background, imprinting a faint polarization pattern that satellites like Planck have detected. Meanwhile, the very transparency the first stars created allows us to see back to their era, a cruel irony, since their light destroyed the conditions that birthed them. Without reionization, astronomers could never have observed the universe's infancy. The cosmic dark ages would still be dark to us, yet mysteries remain. Recent Webb data hints that some early galaxies were too small to account for the speed of reionization, suggesting missing pieces, perhaps undiscovered populations of dwarf galaxies or exotic radiation sources. Each new observation rewrites our understanding of this pivotal era, showing how the universe didn't just wake up, it fought its way into the light, one ionized atom at a time. The cosmic microwave background isn't just a relic of the Big Bang, it's also a cosmic flashlight, illuminating hidden structures as it passes through the universe. One of its most revealing interactions happens when this ancient light plows through galaxy clusters, where superheated gas distorts the CMB's signature in a phenomenon called the Sunyaev-Zeldovich effect. Picture this: photons from the CMB, traveling undisturbed for 13 billion years, suddenly slam into electrons in the million-degree plasma that permeates galaxy clusters. These collisions give the photons an energy boost, subtly altering the CMB's spectrum in a way that betrays the cluster's presence like a fingerprint on glass. What makes this effect so revolutionary is what it reveals about the invisible scaffolding of the cosmos. Galaxy clusters are the universe's largest gravitationally bound structures, but their visible stars and gas account for less than 10% of their total mass. The rest, dark matter, an enigmatic substance that neither emits nor absorbs light. While dark matter itself doesn't interact with the CMB, its gravitational pull shapes the distribution of the hot cluster gas that does. By mapping the Sunyaev-Zeldovich distortions across the sky, astronomers essentially traced dark matter's shadow, uncovering where it concentrates and how it sculpts the universe on the grandest scales. The Atacama Cosmology Telescope and Planck satellite have turned this phenomenon into a powerful tool. Unlike optical surveys that rely on starlight or X-ray telescopes that detect hot gas directly, the Sunyaev-Zeldovich effect works equally well for distant clusters as nearby ones. Their distortion of the SIMB doesn't fade with distance. This lets astronomers discover galaxy clusters billions of light-years away, some so faint they'd otherwise be invisible. In 2013, the South Pole Telescope used this technique to find a massive cluster nicknamed El Gordo, a cosmic heavyweight over 7 quadrillion times the mass of our Sun, lurking 9.7 billion light-years distant. But the real magic lies in the details. By comparing Sunyaev-Zeldovich maps with X-ray and gravitational lensing data, scientists can measure how fast galaxy clusters are moving relative to the CMB, a key test for models of cosmic structure formation. Some clusters show peculiar velocities so large they hint at unseen gravitational tugs from superclusters or cosmic voids, painting a dynamic picture of the universe's large-scale flows. Others reveal shocks and turbulence in their gas, evidence of violent mergers where clusters collide like titans in slow motion. Perhaps most astonishing is how this effect bridges eras. The CMB photons altered today began their journey when the universe was just 380,000 years old, while the galaxy clusters they encounter represent structures that took billions of years to form. Their interaction is a cosmic handshake between the universe's infancy and its maturity, proving that even the oldest light in existence still has secrets to share about how the cosmos grew up. So while the Sunyaev-Zeldovich effect might lack the visual drama of a supernova or quasar, its whispers hold answers to some of cosmology's deepest mysteries, written in the faintest of distortions on the afterglow of creation itself. Imagine the universe in its infancy, so small it could fit in the palm of your hand, yet expanding faster than the speed of light. This wasn't just growth, it was cosmic inflation, a fraction of a second growth spurt so violent it stretched the fabric of space itself thinner than a single atom. In less time than it takes to blink, the universe ballooned from subatomic to cosmic size, smoothing out wrinkles in spacetime and setting the stage for everything that followed. The idea of inflation solves two of cosmology's biggest puzzles. First, the horizon problem. Why is the cosmic microwave background so eerily uniform, with nearly identical temperatures on opposite sides of the sky? Without inflation, these regions would never have had time to thermally equilibrate. They'd be like two strangers on different continents wearing the same outfit by pure coincidence. Inflation's explanation: they were neighbors once, crammed together before the universe's hyper-stretch separated them. Then there's the flatness problem. Measurements show the universe's geometry is astonishingly flat, like a perfectly stretched sheet with no noticeable curvature. For that to happen naturally, the early universe's density had to be fine-tuned to 1 part in a trillion, a probability so slim it's like balancing a pencil on its tip and finding it still standing billions of years later. Inflation's rapid expansion ironed out any curvature, flattening the cosmos like dough under a rolling pin. The mechanism behind this explosive growth: a hypothetical energy field called the inflaton, which temporarily dominated the young universe. Think of it like cosmic repulsion, a sort of anti-gravity that pushed space apart faster and faster. When this field finally decayed, its energy flooded the universe as particles and radiation, reheating it into the fiery plasma of the hot Big Bang. The wrinkles in the inflaton field during this transition weren't erased entirely. They became the seeds for galaxies, imprinted as faint density variations we now see in the cosmic microwave background. Evidence for inflation isn't just theoretical. Telescopes like BICEP and Planck have hunted for its fingerprints in the CMB's polarization patterns, specifically a swirling signature called B mode. While definitive proof remains elusive, The fact that inflation's predictions align so neatly with observations from the universe's flatness to the spectrum of galaxy clusters makes it the leading framework for understanding our cosmic origins. Yet mysteries linger. Was inflation a one-time event, or does it happen eternally, spawning bubble universes in an endless multiverse? Did it begin at the Planck epoch, or was it triggered by some deeper physics we've yet to uncover? The answers might lie in gravitational waves from the universe's first moments, ripples so ancient they'd carry whispers from the dawn of time itself. Until we detect them, inflation remains our best cosmic origin story, a fleeting moment when the universe rewrote the rules of physics to become the vast, structured cosmos we call home. Every star will eventually burn out, every galaxy will drift apart, and in the far, far future, trillions upon trillions of years from now, the universe itself might reach a state of absolute stillness. This isn't just the end of life as we know it, it's the ultimate triumph of entropy, a fate cosmologists call heat death. Picture a cosmos where black holes have evaporated, where protons themselves have decayed, leaving behind only a thin, cold soup of photons and subatomic particles, uniformly spread across an ever-expanding void. No more light, no more heat, just endless, featureless darkness stretching into eternity. But how do we know this grim finale awaits us? It all comes down to thermodynamics, the same laws that govern steam engines and refrigerators. Over incomprehensible timescales, the universe's usable energy will gradually deplete. Stars exhaust their fuel. Galaxies stop forming new ones. Even black holes, the universe's most efficient energy hoarders, slowly leak radiation via Hawking evaporation until they too vanish. Eventually, every possible energy difference, every temperature gradient, every voltage potential evens out. Without these differences, no work can be done. No structure can form. The cosmos becomes a thermodynamic graveyard where even time loses meaning because nothing changes anymore, yet not all theories agree. Some cosmologists propose a far more dramatic alternative, the Big Crunch. In this scenario, the universe's expansion slows, halts, and reverses, collapsing all matter back into a singularity, a mirror image of the Big Bang. This cyclical model suggests our universe might be just one in an endless series, expanding and contracting like a cosmic lung. The math hinges on dark energy's behavior, whether its repulsive force weakens over time, allowing gravity to regain dominance. If it does, galaxies would eventually rush back together, temperatures would soar, and space itself would crumple in a fiery finale. Then perhaps a new Big Bang would birth another universe from the ashes. Then there's the even wilder idea of vacuum decay, the notion that our universe's vacuum isn't truly stable, and a single quantum event could rewrite physics entirely. Picture a bubble of true vacuum expanding at light speed, erasing the laws of nature as we know them. It's a doomsday scenario where heat death isn't the end, just an intermission before reality itself gets rebooted. Between these extremes lie poetic possibilities. Eternal inflation theories suggest new universes constantly sprout from quantum fluctuations, creating a multiverse where heat death is just one outcome among many. String theory proposes higher dimensional brains colliding in cycles of destruction and rebirth, and some models even hint at a big bounce, where the universe avoids total collapse by rebounding into a new expansion phase. What's humbling is realizing that heat death isn't just a theory, it's the default fate if our current understanding holds. The universe's acceleration, driven by dark energy, shows no signs of stopping. Distant galaxies already vanish beyond our cosmic horizon, their light stretched into invisibility. One day, the Milky Way's stellar neighbors will fade too, leaving our descendants, if any survive, with a night sky devoid of anything but darkness. But perhaps there's beauty in this bleakness. Heat death isn't annihilation, it's transformation. Energy isn't destroyed, it's simply rendered inert, like ink diluted in an infinite ocean. And if cyclical models prove true, our universe's death could be just a prelude to rebirth. Either way, these far future visions remind us how fleeting cosmic eras really are. We live in the universe's vibrant youth, surrounded by light and structure, a golden age that, like all things, won't last forever. So while heat death may loom in the unimaginable distance, it also frames our present moment as something rare, precious, and worth marveling at while it lasts. We've journeyed through a universe where stars explode with the energy of 100 suns, where black holes fling galaxies worth of matter into space, and where invisible particles race across the cosmos carrying secrets from the dawn of time. Think about this. In the time it takes you to watch this video, magnetars have unleashed flares powerful enough to strip atmospheres from planets halfway across the Milky Way, while dark matter collisions may have flooded the void with gamma rays we'll never see. Every second, somewhere in the universe, a star dies violently enough to outshine its entire galaxy, or a black hole merges with such force that it shakes the fabric of spacetime itself. Yet here we are, tiny, temporary beings on a pale blue dot, piecing together these cataclysms through faint whispers of light and gravity. That glowing nebula decorating your desktop wallpaper. It's the corpse of a star that died before humans walked the Earth. The gold in your jewelry, forged in a neutron-star collision so violent it bent the laws of physics. Even the static on an old TV contains echoes of the Big Bang, photons that have traveled uninterrupted for 13 billion years to reach your living room. This is the cosmic joke and the cosmic miracle. We're insignificant in scale but extraordinary in our ability to comprehend the universe's grandeur, those gamma-ray bursts that could sterilize planets. We've mapped them, the supermassive black holes that devour stars. We've photographed their shadows, the particles that pass through you unnoticed every second. We've built underground temples to catch them. So tell us, which of these cosmic powerhouses left you awestruck? Was it the quasar jets stretching millions of light years, or the solar flares that could plunge civilizations into darkness? Maybe it's the sobering thought that every atom in your body was forged in stellar explosions long before Earth existed. Drop your favorite fact in the comments, and if you've enjoyed this dive into the universe's most violent playground, hit subscribe. Because in a cosmos this wild, we're just getting started. There are always more mysteries waiting to unravel, more energies to measure, and more wonders to witness on the scale only the universe can provide.